So once they will review the thesis, then only we are allowed to submit the thesis. Yes. I have emailed them. So the paper was there, but now they will be changed to the maintenance. But 4:30. First year, they revised it and they shifted it to maintenance. If you permit, I will do it. You guys, thank you, sir. No, I will be okay. He said he's dying, but he didn't confirm that. After Friday, Friday afternoon, Friday पर इसके बाद the dose provider only from there. All three of this one, Rajiv, Rachan, so they second one is Chinese or Korean? Sir, both are Chinese. Both are Chinese. Rajiv, Rachan from India. So Indian origin or from India? From India only. Yeah. He written that in the August only before. That all completed all the requirements. Try to complete 30-40 minutes. Hello. You will be joining the professor. I actually 10 minutes, 15 minutes before I have again reminded the thing, but I did not really respond. Okay. See your requirement for that. No, sir, it is not that much mandatory. That is very mandatory. For this university, it is not mandatory. I mean, actually, as for the JC, he completed the norms of RMAT. Okay. And for the ACSIR norms, he has to do it. I have separately given the presentation. Hello everyone, my name is Amith. I am here to present my research work on my PhD. my PhD work is on assessment of tunnel soil interaction under dynamic conditions. I am working under Dr. Ganesh Kumar from CSIR, and at RMIT, my supervisors are Jili, Jian Hussain, and Dr. Radhi Royson. And the main motivation for this topic has come from past few failure of tunnels, wherein we could see complete collapse of Daiki station in 1996 due to Colloquium number earthquake, and also the significant collapse of Long tunnel during Wenchen earthquake, wherein we could see complete collapse of lining section, and mostly here, greater than 12% of tunnel in the epicentral area were heavily damaged. So with this motivation, we try to we attempted to understand how the performance of tunnel would behave under earthquake conditions. For that, we have aimed for both experiments and numerical study. So in order to achieve that topic, we have gone through few literatures wherein mostly the literature have been focused on tunnel embedded in dry sand and also in liquefiable sand. But few studies have been conducted in varying saturated sand, and also few literatures have concentrated numerically also, and wherein mostly the shape, thickness, embedment depth, and flexibility ratio have been used for as a parameters for analyzing the tunnel using numerical analysis. So based on this literature, we could see that mostly the frequency and embedment depth of tunnel plays a significant role for understanding the tunnel soil interaction. And also the acceleration showed higher amplification based on the past literature because of the increase in frequency of input motion. So this gap has motivated me to select influence of embedment depth and frequency on behavior of tunnel. And apart from this, we have observed from past literature and also from past case studies that there is a occurrence of continuous repeated shaking events, which has been observed during Tohoku Japan earthquake, Nepal earthquake, Kumamoto earthquake, and Kamamara's earthquake. So and very few studies have been conducted considering the repeated shaking events. And one more significance of the proposed research work is based on the construction of metro tunnel network, particularly in North India, wherein we could see here that during 2020, 2002, only 25 kilometers were operational, whereas during 2022, more than 1,000 kilometers are operational. And mostly these tunnels, which are situated, are in silty sand deposits, and with varying water table, it would affect the structures which is coming over those deposits. So considering all these topic, primary objective, one is considering the economy, considering the extent of economic loss, we formulated the research gaps and objective. And the main objective of this, my PhD topic, is on how investigation on tunnel soil interaction could be done using experiments and numerical studies. For the experimental investigation, I have taken the influence of embedment depth and frequency as a primary parameter on behavior of tunnel in dry sand. And also further, we attempted to understand the influence of varying ground saturation condition on tunnel embedded ground subjected to repeated shaking events. And further, after completing all these experiments, we also try to validate the numerical model using the experiments. And again, we tried to attempted to understand the effect of repeated shaking events, and at the end, how the effect of ground improvement could be effectively used for mitigating the vulnerability of tunnel. So this is the overall view of my PhD work. And when it comes to the approach one, initially the experiments were conducted in dry embedded ground. Particularly, I have chosen relative density of 52% corresponding to medium dense sand, and two embedment depths have been chosen with 5 Hz and 10 Hz frequency. And the input motion used in this study were 0.2G, 0.3G, and 0.4G as a repeated shaking events with 40 seconds duration. For analyzing the tunnel soil interaction response, I have measured acceleration response of soil at different depth, acceleration response of tunnel, dynamic pressure, displacement of soil, and displacement strain on tunnel. So for conducting this study, mostly the soil was characterized as poorly graded, and we also tried to develop a modulus degradation curve using the empirical relationships, and we also validated the developed modulus degradation curve using resonant column test conducted by Maheshwari and Kiran. And we could see here that almost it is coming under similar range of the already available relationships. For the experiments, the shake table have been used, and particularly the dimension of shake table was 2 meter by 2 meter with the payload capacity of 3 ton. And the operational frequency was ranging between 0.01 to 50 Hertz with its acceleration range of 0.01 G to 1 G. The tank dimension for used for the study was 1.7 meter by 1 meter by 0.7 meter. And this is the actual scaling laws which have been used in this study, where 1:10 scale ratio have been used to scale down the tunnel. Accordingly, the dimension of the tunnel is internal length of 270 mm and the external length of 270 mm and length of tunnel of 740 mm according to the specification of a test tank dimension. Yeah, square tunnel.
You're writing diameter over previous slide.
Sorry, sir. That is actually the length actually.
Length of the bottom one. It is a dia.
Width of tunnel. Sorry.
Actually, we have been doing tomorrow, sir. And it also is ready. So repeatedly we put it here.
So this is the instrumentation details which have been used in this study, where 3 accelerometers, 2 earth pressures, and 2 displacement sensors have been used for the both embedment depth. And we have also measured the acceleration response of tunnel by placing 2 accelerometers at the tunnel top and 1 earth pressure cell at the tunnel top. As told earlier, 2 embedment depths have been studied in this research. For conducting the experiments, sample preparation was done using the hopper arrangement with preparation was done layer by layer for achieving the homogeneity. And the last figure shows the prepared tunnel embedded ground, and the below figures shows the sinusoidal input mission which was used in this study, which have been given one after the other after sequentially. Other part of this study is finding out the displacement strain on tunnel using non-contact digital image correlation, wherein we could able to measure the displacement of tunnel by taking a reference image initially before the test. And also we can able to measure deformed images during shaping, and these 2 images were correlated for finding out the displacement of tunnel. And for this we have used VIC 2D software for conducting the experiments. So based on the experiments, we could see here that during 0.2G shaking corresponding to height to bit ratio of 0.85, minimum displacement was observed because of its in situ density. Whereas for the 0.3G shaking, significant amount of maximum settlement was observed, and mainly because densification occurred at this 0.3G, and further doing 0.4G shaking, there is a reduction in soil settlement, which is mainly because of densification which occurred during 0.3G shaking. So mainly here, both frequency and embedment depth and confinement characteristics is playing role. And about 22.9 times higher displacement was observed during 0.3G shaking for height to width ratio of 0.85. Whereas when it comes to height to width ratio of 1.2, initially itself maximum densification occurred, and about this is primarily because there was an increase in frequency for the case of height to width ratio of 1.2, and which affected the displacement response. And we also measured the acceleration response of tunnel. From this figure, we could see that the front end of tunnel showed higher acceleration response compared to the rear end of tunnel, and also with increase in frequency, the acceleration response has also increased. This is primarily due to the non-uniform densification which occurred due to shaking, which affects the acceleration response of tunnel. We also measured the acceleration response within the soil, and from these figures, we could see that with increase in embedment depth, acceleration response is also increased, and also at shallow depth, there is a higher acceleration response primarily due to the soil nonlinearity. And for the 5 Hz frequency, about 34 to 58% increment in acceleration response was observed. And for the case of height to width ratio of 1.2, the about 17.9 to 33% higher acceleration response was observed at different depths. We also measured the displacement of tunnel using digital image correlation, and we could see here that with increase in input motion, the displacement has increased for the case of height to width ratio of 0.85, and which is the similar trend have been observed for the case of height to width ratio of 1.2, although higher displacement was observed during for the case of 5 Hz frequency. We also this is the reduction in displacement is primarily because of higher confinement characteristics for the height to width ratio of 1.2, which affected the displacement response. We also measured the strain, and using the strain response, we can see that for the 5 Hz frequency, increment has been observed for the case of 0.2G, 0.3G, and 0.4G shaking, whereas after 0.3G shaking for the case of height to width ratio of 1.2, sudden reduction in strain have been observed for the 0.4G shaking. So this could be related to the development of earth pressure, which affected the tunnel soil interaction response. Primarily because of the variation in the stress variation between the tunnel and the surrounding soil, the strain also varied. So based on this study, we could conclude here that the application of 5 Hz frequency during repeated shaking induces an increment in soil densification, which contributed in overburden stress around the tunnel system, which affected the response. Similarly, at for about 14 to 58% increment in dynamic earth pressure was found up to 0.3G loading for both embedment depth conditions. In the case of height to width ratio of 0.85 when subjected to incremental shaking, there is a steep increment in strain which was observed from 0.2G to 0.4G shaking, mainly because of the lower confinement. And in the case of height to width ratio of 1.2, the reduction in strain at higher acceleration loading is due to improved confinement offered by the adjacent ground. So this research has been published in International Journal of Geotechnical Engineering in 2023. Further, after conducting this study, we thought of understanding how the saturation would play a role in affecting the soil interaction response. So in order to understand that, we have taken both square tunnel and circular tunnel as our objective, wherein for the case of square tunnel, 25%, 50, 75, and 100 for the varying saturation test cases. wherein the sinusoidal waves from 0.1G to 0.5G shaking have been given as an input with corresponding to 5 Hz frequency. Here also we try to measure the tunnel soil interaction response by measuring acceleration response at different depth, pore water pressure, dynamic earth pressure, displacement of soil, and displacement of tunnel. When it comes to circular tunnel, similarly, we attempted to understand whether would there be any changes. So we varied the saturation of 50, 75, and 100 saturation, and here we have varied the scale down earthquake of Kobe, El Centro, Chichi, and Japan earthquake. And all these 4 earthquakes have been used as a repeated earthquake motion. So for conducting this test, initially gypsum have been used for sample preparation of scale down tunnel, and similar to the previous cases, we have used hopper arrangement for sample preparation, and wet sedimentation technique have been used for achieving the saturation. The sand used was Solene sand, which is similar to the previous objective, and 4 pore pressure sensors, 2 accelerometers, 3 earth pressure cells have been used along with 1 displacement sensors for monitoring the variation in response. And as told earlier, the input motion used in this study is from 0.1G to 0.5G, and we have given 24 hours as a dissipation time for water pressure to dissipate. And after
Sequential loading.
yes, yes,
First point when we then stop and point to the same setup.
yes. For the same model, instead of changing the model, we have given for the same
Sequential rounding.
sequential. Okay. So based on the experiments, we actually used only 2 accelerometers and displacement sensors as told earlier. And for the shallow depth, higher acceleration response were observed compared to deeper depths. And also we could see from the graph that for the up to 0.3G at shallow depth, higher acceleration response have been observed, and beyond which there is a drastic reduction in acceleration response at shallow depth. Similarly, for the case of deeper depth, we could see here that the acceleration response has increased with respect to input motion. This variation is primarily because of non-uniform densification and also because of the soil non-linearity which could develop due to the repeated shaking. And the other part of the reason for after 0.3 shaking, the reduction is primarily due to the soil settlement, which beyond after 0.3 shaking, it has drastically reduced, which affected the acceleration response also. We measured the pore water pressure, and based on the pore water pressure, we estimated the pore water pressure ratio, and we could see here that for the case of 25% saturation, no much significant increase in pore water pressure have been observed, whereas for the 50 and 75% saturation, slightly increment in pore pressure has been observed. Although there is no liquefaction was observed, for the case of 0.3G and 0.4G subsequent shaking, we could see because of the shaking history, liquefaction and accompanied by for the case of 0.3G and 0.4G subsequent shaking, we observed almost complete liquefaction. Complete liquefaction for the case of 0.3G and 0.4G shaking, which primarily due to the shaking history and duration of shaking, which primarily played a major role for occurrence of liquefaction. This continued even after 0.4G shaking also. For the case of 75% saturated ground condition, because of this development of pore water pressure at different depths, the peak displacement of tunnel increased with respect to input motion. And based on these experiments, we also observed physically that there is a longitudinal crack for the case of 50% saturation, which affected the stability of tunnel. And also we observed complete heave of ground surface for the case of 75% saturated test series. So we also conducted the test for the fully saturated ground, and we observed that during 0.2G itself, maximum settlement was observed, and this affected the pore water pressure at different depths. And we could see here that from based on this graph, until 0.3G shaking, maximum pore pressure ratio have been observed, and at 0.3G almost liquefaction has been occurred based on the pore pressure ratio. But after 0.3G shaking, we could observe that there is a slight reduction in pore pressure. This is primarily due to the displacement of tunnel, vertical displacement which occurred during 0.2G to 0.4G shaking, which affected the pore pressure ratio. So based on these all varying saturated ground, we could infer that the acceleration response variation at different depths highlighted the occurrence of non-uniform soil densification, and influence of saturation affected the major role for tunnel soil interaction response. And based on the pore pressure ratio, primarily due to the influence of repeated shaking history, and the soil saturation affected the acceleration response, and liquefaction and reliquefaction occurred during 0.3G to 0.5G shaking. About 1.2 to 1.7 times and 1.6 to 1.93 times higher displacement was observed, which is primarily due to the pore pressure development at different depths. So based on the fully saturated ground, we could infer that up to 0.3G shaking with limited embedment depth, tunnel uplift was observed. At 0.4G and 0.5G shaking, the stability of tunnel reduced by about 15% to 89%, which induced variation in stress transfer between the tunnel and adjoining ground developed after shaking. So primarily, even for the fully saturated ground, soil saturated affected the tunnel soil interaction response, and mainly because irrespective of the minimum generation of pore water pressure during 0.1G shaking, the induced disturbances during 0.1G shaking resulted in tunnel upliftment for the 0.2G shaking. So overall, what I want to conclude here is primarily because of shaking history, the tunnel soil interaction and liquefaction along with reliquefaction is occurring during the repeated shaking events. So after conducting all these experiments, we thought let us go for how scale on earthquake will affect the tunnel soil interaction response. Here, since for the previous case, we could not able to measure much pore water pressure increment for the 25% saturation. We only concentrated on 50, 75, and 100% varying saturation, with 52% as a relative dense ground. Here, we for the scale down tunnel, we locally available concrete tunnel have been taken, and which has a internal dimension of 195 mm and external diameter of 245 mm, with the length of tunnel as 740 mm. Here, mainly duration have been scaled down in order to simulate the earthquake condition in the shake table. So similar to the previous case of preparation of sample, we also prepared similar way for the circular tunnel also. Here we have used 4 pore pressure, 4 accelerometers, and 3 earth pressure sensors for measuring the tunnel soil interaction response. And we also used DIC setup for measuring the displacement of tunnel. This is the details of the input motion which has been used in this study, wherein Kobe earthquake, Imperial Valley earthquake, Chichi earthquake, and Tohoku earthquake have been used sequentially one after the other, with simulating 2 foreshocks, mean shocks, and aftershock events. Based on the experiments, we could observe here that at shallow depth there is higher acceleration response, and mid depth there is slight reduction in acceleration response, and at deeper depth significant lower response have been observed. This is primarily due to soil nonlinearity and also due to the densification which could occur because of the existence of tunnel. So this graph indicates how tunnel soil interaction would take place. Initially, when we give input motion, disturbance will occur, and because of the disturbance, soil settlement occurs at ground surface, and because of this disturbance, pore water pressure generation occurs, and due to the generation of pore water pressure, complete confinement characteristics will break, and due to which the tunnel displacement will be higher. So we observed increment in pore water pressure with respect to input motion, and higher pore pressure have been observed, which is obvious with increasing depth. Due to continuous shaking, disturbance in the ground causes pore water pressure generation, and the pore water pressure generation during shaking encourages tunnel displacement. So here, similar to the previous case, primarily because of soil saturation and shaking duration, tunnel soil interaction affected the generation of pore water pressure. We measured the displacement of tunnel, and this is obvious because of the loss of confinement. Displacement increased with respect to input motion and also with respect to saturation. And based on the these experiments, we inferred that acceleration intensity contributed significantly in inducing the tunnel deformation in addition to shaking duration. And higher the acceleration intensity, time for pore water pressure generation found lesser, affecting the confinement characteristics of the ground. As told earlier, soil saturation significantly influenced the dynamic performance of tunnel during repeated shaking. From the estimated pore pressure ratio, it is evident that influence of saturation induced liquefaction of soil, and at higher acceleration amplitude, soil liquefaction around the tunnel was observed, even though soil densification achieved during initial repeated shaking. So based on this study, because of repeated shaking, obviously tunnel undergone more displacement and strain. After conducting these experiments, this is the part of the work which I completed at RMIT, wherein we used all the details of experiments in order to validate the numerical model. For the numerical model, I have used UVC 3D PLM model, and two parametric studies have been conducted. Initially for effect of repeated checking have been justified, and also effect of ground improvement have been studied in this research. For conducting the numerical model validation, we use similar dimension as that of shaking table, and primarily based on the SPT n value, all the parameters have been calculated using Flaxis 3D. These empirical equations have been given in the Flaxis 3D manual for calculating the input parameters, and mainly linear elastic plate element have been used for modeling the tunnel, and interface reduction factor of 0.66 have been used for simulating the interface between tunnel and soil. And these are the details of dynamic boundary conditions and static boundary conditions, wherein the bottom boundary was completely fixed, and compliant based boundary have been used at the bottom for simulating the earthquake. Here, Kobe earthquake have been used as a part of input motion, and Rayleigh damping coefficients have been calculated for in order to accommodate the soil nonlinearity. This is the graph which shows the numerical validation, wherein we try to measure the acceleration response at different depth, pore water pressure, displacement of soil at ground surface, and tunnel displacement. Based on this validation, we could see around 10 to 15% deviation was observed between the numerical model chosen and experimental study conducted. And after conducting this validation, we still again went for further studies to simulate in full scale. So in order to analyze the numerical model in full scale, we have used the scaling factors according to 1:20 ratio, and all the parameters have been calculated. And this is the full scale numerical model, which is exactly scaled up as per the scaling laws. And again, the input parameters have been calculated based on SPT n value, and the relative density of ground simulated is similar to the medium dense ground condition in prototype scale. So based on this study, based on this study, we have chosen for for the part of ground improvement, I have chosen sorry. The first part of the parametric study was to simulate the repeated shaking. We could see from the left graph that this is the pore water pressure development which observed for the 0.5 G individual shaking, and we could see here that almost 40 kPa maximum pore water pressure have been observed, and correspondingly the tunnel displacement observed was around 40 mm. But whereas for the repeated shaking 0.5 G after 0.2 G, we could see that although there is significant improvement in excess pore pressure development up to 38 kPa, which is comparatively lesser for individual shaking, but still we could observe maximum displacement of up to 80 mm. 80 mm for the case of 0.5 G shaking after 0.2 G. This justifies that repeated shaking is highly intense compared to the individual shaking. After conducting this, we also tried to adopt a ground improvement technique for whether it could mitigate the vulnerability of tunnel, and particularly stone columns of permeability 2 into 10 power minus 5 meter per second, and sand of permeability 2 into 10 power minus 5 meter per second have been this value actually it is comparatively lower, and based on these are the four installation schemes which have been adopted for the conducting the numerical study, wherein initially ground improvement have been conducted for initial 5 meter, and then we also went for 10 meter complete depth ground improvement. And
You explain this very quickly. I have my doubt.
sir, one way of finding the HCT value is information is having given the black experiment where N1 60.225 will give the relative density of the company.
So you have related density, so from that important.
Yes. That is one way. And the second way is based on Howard's textbook, there is a relation between relative density and density engineering. And we could also choose from there if density and value is not available. Yes. For conducting the ground improvement technique, initially 2 rows with 10 columns of stone column have been used, and also 8 columns of 10 stone columns have been used, and 2 ground improvement have been conducted for the 2 different depths. One is 5 meter and 10 meter, and the input motion used in this study is also Kobe earthquake. And we could see here that for the case of ground improvement up to 5 meter, having configuration of 10 cross 2, there is no much reduction. Whereas for the case of 10 cross 8 configuration with for the ground improvement up to 5 meter and 10 meter, there is a almost 39% reduction in soil settlement. And we also measured the uplift displacement of tunnel, wherein we could see that almost 58% reduction in tunnel upliftment has been observed for the case of 8 cross 10 configuration, particularly for both 5 meter and 10 meter ground improvement. We also measured the pore pressure ratio for tunnel embedded ground, and we could see that for the case of 5 meter, there is no much reduction in pore pressure, whereas for the case of 10 meter ground improvement, only at the shallow depth, there is significant reduction in pore pressure ratio, whereas pore pressure increased at deeper depths. So from this, I can able to conclude from the numerical investigation that although 10 cross 2 column have been did not found effective for mitigating the upliftment of tunnel, for the case of 10 cross 8 configuration, we could see drastic reduction in tunnel displacement and also pore pressure ratio. So this is the complete overview of my PhD work, and I would like to conclude here with a future scope of the study with the observed response of all these experiments could be used for monitoring the real-time monitoring of tunnel structures, and we could also conduct a centrifuge study for particularly in layered soil and slopey strata, because there is no much study on slopey strata. And we could also extend this study for the development of fragility curve to assess the performance of tunnel under earthquake conditions. Through numerical investigation, different ground improvements here, only limited ground improvements have been observed, conducted based on the time availability. Different configurations of ground improvement can be used for further studies. So these are the details of my publication. 2 publications have been published in European Journal of Environmental and Civil Engineering, and also in International Journal of Geotechnical Engineering. And 2 are currently under review, and 2 are at the preparation stage. And 3 book chapters have been published based on the study conducted, and 3 conference paper I have written during 2021 to 2023. And this is the overall view of my PhD. And this is the overall view of thesis outline, wherein I have formulated my thesis for 6 chapters, wherein the first 3 chapters devotes to introduction, literature review, and experimental methodology. And chapter 4 and chapter 5 are experimental and numerical investigations. And chapter 6 is conclusion and future recommendations. The existing topic, the title of my topic is assessment of tunnel soil interaction under dynamic conditions. I would need suggestions in case if there is any changes could be done based on my work. And I would like to thank everyone, both at AcSIR and also at RMIT, and including the fellowship both at India and Australia. And particularly, I would like to thank the coordinator and DAC members, and also the technical support I got from Sheikh Table, particularly DIC. He was completely available all the time. And I also particularly thank all the co-researchers, both under my supervisor and also with Dr. Manoj Samanta sir for helping out in between. And also, I would like to extend my thanks to all the laborers who are able to available for conducting the study till 6 p.m. In the evening. So I would like to end here. If there is any questions, please.
It's very good work and extensive work. Okay, I have two queries. Could be understand more. Can you start with your model project, model, picture of your model, image plan. You are saying h by w of 0.85 and 1.2. What is h here? From where you are getting the h from the vector of the summing or from your model?
1. Yeah.
H is from where?
H is from here to here.
Top of the summing. From ground to top of the place. That be your h you are saying. Okay.
And as per the literature, if the height to width ratio is less than 1.5, it is considered as shallow tunnel.
Secondly, first your first part was on square tunneling. Here also the question was sequential or it was individual?
This is incremental, sequential incremental shaping.
Okay, in this case,
In this case,
if that's why you get to 0.4 G, this amount
yes.
is related because of maybe the complexity.
Yes.
And go to numerical work and the numerical work. Up there. So over the ground implement part, yeah. How you give you stone coordinates?
Yes.
If you use stone column, it's in different patterns. So it's 8 by how much?
8 by 10, like 2 column
10.
and 10.
Diameter of the stone column is
Diameter of stone column is 200 mm.
200. And spacing
Spacing 3 meters meter.
in each column.
Yes.
200 and 10 meters.
It was taken in such a way that the ratio between the stone column and the spacing is L by T ratio of 2. L by T ratio 2.
Diameter. What is the diameter?
200
Diameter of the
mm.
program is 3
And spacing is 3 meters. That is 2 meters in India. But normally spacing.
That is.
Sorry,
Diameter
diameter is 500 mm.
Okay.
Diameter is 3 meters.
Okay. And 10 meters spacing.
Yes.
It is direct. The effective should be less than that. Okay. And how many rows? Then you are changing this number of rows also. 1 is 2,
Then 4 this side, 4 left side.
Okay. Difference between these two, and then their depth.
Yes, depth, like initially 5 meter ground improvement and 10 meter ground improvement, particularly up to the tunnel wall.
5 meters, you will not get quite different. Like we need top of it. Should be up to the bottom. It is there, it should be up to bottom. Okay. Otherwise, there is no reason. Okay. And you will get any difference. Any difference is there between the 5 meter stone column and the without stone column, and difference can you compare
Without stone column,
without stone column and only 5 meter stone column. What is the difference? Can you compare?
without ground improvement, this is the vertical displacement of tunnel.
Okay.
And with ground improvement for the case of 2x10 configuration, there is no much reduction, although 18% to 30% reduction is there. But for the case of 10 meter ground improvement and configuration of 8 for 10, almost 58% reduction.
And number of rows, there is respect of only number of rows also. 8. Okay. What about pore pressure?
For pore pressure for the 5 meter ground improvement, there is no much significant reduction in pore pressure. But for the case of 10-meter ground improvement with a configuration of 8x10 store column arrangement, at shallow depth, significant reduction is there, but again at deeper depth, no much significant reduction.
You have to 5 meter also, right? Let's 10 meters, then bottom. Okay. Really going to 1.0. Okay. That is 2.5 meter depth. Okay. The black one is 2.5 meter.
2.5.
5 meter and 10 meter is less than 4 meter. What is this case? It's without stone column. Okay.
These two are without stone column.
Okay. And next is at 2.5 meter is 5 meter. 5 meter, 2 and 10 meter. Are you reaching 1? Here it was not there, or what? What is maximum RU max in the case of without stone column for 5 meter and 10 meter?
For the 5.8 and
Somewhere 0.8 and somewhere 1.6.
You pick a marker.
But okay, but here what is RU max in this case? For 5 meter, you have almost 1. And 10 meter, again between 1. What that means?
only at the shallow depth for this 2x10 configuration, only at shallow depth is 23.
That's not affecting. Still, it's happening like this. Any reasons for that?
Professor, probably this could be due to the permeability which I have used. That if I reduce the permeability of stone column, the effectiveness will be low.
Why is it insignificant? You try to answer that one. Permeability is not the case.
Maybe it is greater than the without stone column now. Yeah, that is the reason. Why?
Mainly because of the spacing which I have used, that is not effective for water pressure dissipation.
Spacing, area replacement ratio, or depth of improvement, number of columns. That you tell me that may quantify.
Mainly this is because of the embedment depth I have chosen only up to 5 meters, and I'm expecting the ground improvement up to 10 meters, so there is no much reduction. And the other part is the area replacement ratio. If I'm using only 2 columns, there is no much significant because only 5% area replacement ratio I'm using. So further could be extended to
That is for 8x10. 8x10 is there. Okay. 8x10 a little bit better, no?
yes,
Yeah. 5 meter better. 10 meter again going to 10 meter. Okay. And the bottom of the condition you have
17 meters.
Tennis condition at the bottom. But it can.
Sorry,
Tennis condition at the bottom plane.
it is completely fixed.
Which of only tennis not to the bottom. That is very too fast, but still. Then it should not be, it should happen here also actually.
Actually, this is the one thing it I did RMA.
Okay.
That proposes.
What? Problem is the tennis length of tennis part, but that should be reflected here also in this case also. Okay. Look from my study. But try to see some more better justification for it.
Take that one. Okay. You also discuss with proposals RMA regarding this.
What boundary conditions you have taken in this case?
We field boundary condition for the lateral boundary.
Okay. So viscous boundary that
Viscous.
and the bottom one.
Bottom was completely fixed with
Someone taken compliance boundary. Okay. The fixed one. Okay.
a concrete fish I have used for in the input mostly.
Okay. Okay. And what are the properties of this stone column material you are taking? Permeability and
this is what I told in between the presentation, Professor. This is the sand. This actually I have written wrong.
okay.
The sand permeability and stone column permeability is almost in the ratio of 200 times.
Okay. Effects. And what about the angle here? That is angle is for sand and stone column. What is the angle of permeability?
Uh, 40 degree and 37 degree.
And so it's the direction for mobilize direction and only some down. Direction mobilize for different will down. It's a become
Because that needs to be signed 4 to 5 papers. Like,
okay.
and we will protect it.
Have the print.
No, that you have to get it signed through places. You have to write the title, everything. You have to get exactly.
Can I add something, sir? Like I have written all the details and
No, the title has to be discussed with other BSc members also.
Okay, I actually
Because that is.
sorry, Professor, I just want to, sorry for interruption. I just want to ask if there is any changes for the topic.
You better ask that one first.
Okay, sorry.
but its work is good. So you can have some more clarification. Just keep on trying. That part. Maybe spacing is too much. I think normally phone call the maximum go up to 3D only. FID so
Actually, this is the first one going for RMIT from KC. So the thing is like that professor also was on isolated KC. We don't have much interaction when we had a combined discussion. I also surprised to see when having their final difference. That time only he had told the So previously it has been discussed over the. That's why I say like if in 1 year he gets there, you have to publish along with them. So that part they have given this work to give as part of that program.
Okay, one numerical model you can maybe reduce spacing. Okay. Maybe spacing you can maximum up to 3D only. In this case, if you are taking how much? If it's 500 diameter and 3 meter, 6 yeah. Make it reduce it and just see whether what kind you are getting.
Please talk with them. Numerical experimental, there is a variation in 10 to 15% of report. After that, is it in the acceptable range?
Sir, I will keep it on and I will comment after you. Actually, I was not aware that my supervisor is so I will message and I will come to you.
Fine, sure. So, क्या बोला? हाँ सब लोग जा रहे हैं.
Hello, Amith. Are you there?
Yeah, yes, Professor, I am here.
Hey, great. I think everything's good, right?
Yeah, everything is good. My Indian supervisor has just gone out. I will call him a minute. Could you please wait, Professor?
No, that's fine. That's fine. I think as long as you finish your final a defense, that should be fine. So, do you need my assistance?
Not particularly, Professor. Currently not needed, but still I might discuss with you based on the doctoral advisory committee.
Yeah, I think several researchers are interested in the review panels, interested in the simulation on the ground improvement.
Yes, Professor.
Great, great.
So based on the input given, I would like to discuss maybe 1 or 2 days after. I will mail you for the discussion.
Okay, sure.
Yeah, thank you, Professor. Sorry, I would like to call my supervisor once. Could you please wait for 1 minute?
Okay. Hello.
Hello.
So nice to meet you.
Yeah, Professor, when you joined?
Yeah, I joined. Probably I just finished a meeting at around 4. So I
Oh,
joined
sorry.
maybe 8 minutes later.
Oh, I'm sorry, Professor. I didn't notice that. I'm sorry.
No worries, no worries. I arrived late anyway.
Okay. And have you seen his presentation, Professor?
It's pretty good. He explained everything well. Yeah.
And if you have any comments, you can please ask him. No problem.
Sure, I will. Probably we have lots of discussion when he's in Melbourne, and then yeah, we address a lot of issues in his simulation.
Okay.
Yeah, I think you have a very good student.
Yeah. So hopefully we will meet soon. Please try to come to CBRI for a visit.
Okay, sure. If it is a chance, I will.
Sure. Okay, Professor.
Okay, thank you. See you around.
Yeah,
Bye.
thank you, Professor. Yeah.